Hi there, my name is Professor Richard Riley and this is my talk for MEMTAB 2020. So I'm talking about IPD meta-analysis to examine treatment covariate interactions, and I'd like to thank my collaborators that are listed on the screen. So in this talk I'm motivated by precision medicine, which is trying to tailor treatment decisions to individuals based on their characteristics. A classic example is tamoxifen, which is recommended for those that are estrogen receptor positive, because the treatment is shown to work well in those that are positive, but not so well in those that are negative. So here we're looking at IPD meta-analysis to identify interactions like this. So for brevity, I'm going to assume everyone knows what an IPD meta-analysis is, and I'm going to focus on how we do this type of approach correctly to estimate interactions. And I'll introduce fundamental methods and highlight key learning points about how we can do things better. And this is all based on a paper that came out recently in Statistics in Medicine. So what are the fundamental statistical methods for IPD meta-analysis? The main approach I would recommend for IPD meta-analysis is a two-stage approach. This is where in the first stage you analyse each trial separately, estimate the treatment covariate interactions in each trial, and in the second stage you pool those in a standard meta-analysis like a random effects meta-analysis. On the screen I've got an example for it with a continuous outcome. And so essentially in the first stage you'd fit an analysis of covariance type model, adjust for baseline, estimate an interaction term here denoted by gamma W, where W means within trial information, and I'll come back onto that later. And then the second stage you pool the estimates of gamma W across studies to get an overall average interaction between treatment and the covariate of interest. The alternative is a one-stage approach where we fit, for example, a mixed model that accounts for the clustering of participants and analyses all the IPD from all the studies all in one go. So I've got an example on the screen there of a one-stage IPD model that's got an interaction included, gamma W again. The key thing here is that I've stratified all the nuisance parameters, the intercepts, the adjustment terms by trial. And this means that we make sure that our interaction is based only on within trial information, which is important, and I'll come back onto that later. So let's look at an example. We did an IPD meta-analysis of 10 trials of antihypertensive treatment, and across these 10 trials there was overall benefit, clear benefit, that this treatment is effective overall. Reduction in blood pressure compared to control of about 10 millimeters of mercury. But the question is this consistent for males and females? So we looked at a two-stage meta-analysis of the interactions between treatment and sex. And when we pool these interactions across studies, we get a pooled interaction of 0.77, which is a very tiny difference in the treatment effect on the blood pressure scale. And indeed, it's not clinically relevant. The confidence interval encompasses 0, so there's no evidence here of an interaction between males and females and treatment effect. Incidentally, if we've done a one-stage approach, you get exactly the same answer, and that should usually be the case, unless you've changed estimation methods or unless the outcome is rare. Okay, now let's look at some fun stuff, which is where things go wrong and the problems that we can encounter when doing IPD meta-analysis badly. 7 pitfalls and learning points. The first key learning point is not to do a meta-analysis for each subgroup separately and then compare the results. So don't do a meta-analysis for males and then compare that result to a meta-analysis for females. It looks simple, but it's wrong, because let's think of an extreme example. If you had a study that only recruited male participants, then that has no information about the difference between males and females, because no females were in the study. However, if you did the subgroup comparison approach, then it would be included because it would contribute to the male-only subgroup meta-analysis. So if you look at the bottom there, I've got an example where you do get a difference. If you take that approach, you get 1.57 compared to our estimate before, which was 0.77. So a double of the effect size. So don't do that. The second learning point is to stress that we must separate out within trial and cross-trial information in a one-stage meta-analysis. So what people often do is just to include a interaction term without stratifying by study or without centering your covariate. And what this does is it leads to an amalgamation between within trial and across trial information. And by across trial information, I mean at the meta-regression level, essentially, the relationship across studies. And this leads to bias. For example, here at the bottom, I've got in the hypertension example again, but now looking at an interaction with age, when you account for, when you allow there to be a cross-trial information involved, you get an effect size that's about twice the size as the one based on within trial information alone, and the statistical significance is changed dramatically. And this is because the cross-trial information is subject to study level confounding. For example, studies with a older age group of patients may also have had a higher dose of the drug, and therefore you introduce this confounding that's not there at the participant level, and therefore we need to focus on within trial information. Learning point 3, do not dichotomize continuous covariates or indeed outcomes. You just lose information, it's biologically implausible, it leads to data dredging, and it's against the ethos of precision medicine. Here's an example. Pregnancy, we did a IPD meta-analysis in pregnancy to look at the effects of interventions to reduce unnecessary weight gain. When age was analysed on its continuous scale, there was strong evidence of a relationship, an interaction between age and the intervention effects. When age was dichotomized at 35, which had been suggested to us, then there wasn't anywhere near as strong evidence of a relationship between age and treatment effects. So you lose information and you can potentially miss something that's important. Learning point 4 is that interactions may actually be nonlinear. So if you've got a continuous covariate, the previous slides I've assumed a linear relationship, but actually it may be nonlinear. So in this example here, what I'm showing you is that the treatment effect on systolic blood pressure may be not as strong in those that are younger compared to those that are older. So my reference group here is people that are age 55, and below 55 there seems to be strong evidence of a difference in the treatment effect for those that are younger compared to 55. And we can get graphs like this by doing a multivariate meta-analysis. So we pull, for example, a spline function across studies, and in the paper we talk about how to do that. I think sometimes we may be missing interactions because we're not looking at nonlinear relationships. Learning point 5 is to emphasize that a treatment covariate interaction may exist even when there is no heterogeneity in the overall treatment effect. And indeed, heterogeneity in the overall treatment effect is a really poor indicator of whether an interaction does exist or not. So let's have a look at an example. In the hypertension dataset again, we looked to see whether there was an interaction between baseline blood pressure and the treatment effect on cardiovascular disease. When we looked at the overall treatment effect on cardiovascular disease, there was no evidence of any heterogeneity. There was strong evidence the treatment was effective, but tau squared was 0, no evidence of heterogeneity in the overall treatment effects. But when we look at a nonlinear interaction between systolic blood pressure and treatment effect, we see, similar to the graph before with age, that in those that have a lower baseline systolic blood pressure, the treatment effect seems to be less strong compared to here a reference group of a baseline blood pressure of about 140, and also as you get older, the treatment effect seems to get even stronger, which you might expect. So there's no heterogeneity in the overall effect, but there does seem to be an interaction between treatment and baseline blood pressure in this example. The sixth learning point is very simple. It's basically to emphasize that even if a treatment covariate interaction exists, that the treatment may still work well for everybody. So look at this graph. We can see that I'm predicting on the y-axis the treatment effect on blood pressure, and on the x-axis it's conditional on age. And what we see is that the predicted treatment effect is always negative, i.e. it's going to reduce blood pressure more than control for everybody. Yes, it may work better for some people than others, but it works for everybody, and that's something we need to remember when we're making our decisions and our conclusions after we identify an interaction. And the last learning point is to suggest to people that to start calculating power of IPD meta-analyses in advance of actually doing the project. So based on the amount of IPD that's been promised, what is the potential power of your analysis? So in our paper we talk about how you do this, and NSOR's proposed a simulation-based approach. Closed form solutions are possible, and in the paper we give an example where, based on 24 trials that promised their IPD, we calculated that the power to detect an interaction between BMI and treatment effect was about 83%, which would have been really valuable to know in advance of doing the project, and indeed funders would also benefit from knowing that. In conclusion, IPD meta-analysis projects are so important in this area, but we need to be doing them better. We need to focus on within trial interactions, we need to handle continuous covariates and continuous outcomes appropriately. And in the paper we talk about other issues that you may also find interesting, such as adjusting for prognostic factors and the scale of analysis. Thanks for listening. And I'll leave you with some references and information about courses at Keele, but in particular to draw attention to our new website, prognosisresearch.com, which is aiming to improve prognosis research standards by giving a foundation of good practice, latest methods, tutorials and videos, and would really welcome your feedback.